All right, today what we're going to look at are, Unit 4, Lesson 6. This is our last lesson of the unit, and we are going to be comparing whether looking at word problems, tables, and graphs, and we're going to determine if a function is either linear or exponential. So what I want to do is I want to start out by looking at numbers 3 and 6 very quickly with you. Both of these are graphs, and so if you had to determine which one you thought was linear and which one you thought was exponential, take a minute and just think about which you would choose and why. So I'm hoping that everybody determined that number 6 was linear. And why would you have said that it was linear? Well, it is a perfectly straight line. Okay? Linear, remember, means straight line. Number 3 is going to be an exponential model. Exponential. And you know that by looking at it because it has this curve. Okay? So exponential has a curve. Linear is a perfectly straight line. Now, let's look at our tables, okay? When I look at a table, the first thing that I try to do is find a linear model from it. So if I did 27 minus 9 and then 9 minus 3, would I get the same numbers? And the answer is no. 9 minus 3 is 6, but 27 minus 9 would give me 18. So those numbers are very different. So if I can't do this by subtraction, then I want to try to do it by division. So 27 divided by 9 is 3. 9 divided by 3 is 3. 3 divided by 1 is 3. So if I find a common ratio via division, then this is going to be exponential. Exponential. All right. Now let's look at number 4. If I, again, try subtraction, 23 minus 18 is 5. And then 13 minus 8 is 5. So I'm doing this by subtraction. 28 minus 23 is 5. So if I can find a common difference, then it's linear. So I do want to add this note here, okay? So linear has a common difference, and exponential has a common ratio. Remember, a ratio is in fraction form for us. All right, so we've done it from a graph, we've done it from some tables, and now we're about to do it from word problems. All right, so number 1, you have $20 for iTunes on a gift card, and you decide to buy some songs for $1 per song. All right, so that's my keyword there. Now let's look at number 5 and see if we can find our keyword or phrase there. You wake up with 2 chicken pox, and each day the number of chicken pox that you have triples. Okay, so that's our key phrase for our number 5. Triples and then $1 per. So based on those phrases, which one do you think would be exponential and which one would be linear? If something is happening per, if you remember when we were writing linear equations, per is like 1 per song. All right. So this is linear. Same key phrases that we're used to. But if you see the word triples or doubles or decreases by half per, then it's going to be exponential. All right. So we have now done one linear and one exponential for word problems, for tables, and for graphs. And we've done those together. Now I'm going to ask you to pause your video and see if you can determine which is linear, which is exponential from these 6 problems. So I want you to pause the video and give that a try. So hopefully you were able to, looking at the graphs, find the curve really quickly and easily in number 7 and see that number 10 is a perfectly straight line. Let's look at 9 and 11. I told you that I always start out by trying to find a common difference. In number 9, I was able to do that. So my common difference was 4. In number 11, I tried to find a common difference. I did 100 minus 20 and I got 80. And then I did 20 minus 4 and I got 16. So it did not have a common difference. So then I tried a common ratio. So 500 divided by 100, 100 divided by 20, and I was getting 5 for all of them. So they had a common ratio, which makes them exponential. All right. Number 12, your cell phone plan is $25 a month plus 10 cents for each minute over your allowance. I was able to write a linear model for that right here. I just went ahead and translated it and I wrote it up. And so that would have fit perfectly into our linear functions unit. However, number 8 would not have. If you buy 3 dozen donuts and each day your family eats half of them, other than diabetes, we need to figure out what kind of function this will lead to, right? So I went ahead and I made like a little mini table here where 36 represented my 3 dozen donuts and the 1 under it would be day number 1. And then if they eat half, half of 36 is 18. And then for day 3, half of 18 gave me 9. And then half of 9 would be 4.5. And you could keep going. So this is being multiplied by 1/2 each day, which makes that 1/2, it's not a common difference, it is a common ratio. Remember, a ratio can be represented as a fraction. So number 8 was exponential. All right. Now let's go look at our example number 13 over here. And let's try not to get a little too crazy with everything going on now. This example is one that I've been using for several years, okay? This is comparing a biohealth company is trying to eliminate the flu. In their research, they have come across 2 different strands of the flu. The first strand attacks cells at a rate of 50 cells per hour. A rate of 50 cells per hour, and that is strand A. And I can see in hour 0, there was 0 cells that were killed or attacked, okay? In hour 1, we now have 50 cells that were attacked. How many cells would there be attacked in hour 2? And so I would add 50. How about in hour 3? 150. 200, 250. So I want you to think about what kind of function this is. And this would be a linear function because if I subtracted anywhere, I could pick any numbers to subtract and they would all give me 50. All right. They have a common difference. I guess I should finish filling in my table. And then we're about to go look at strand B. So let me just write here that this is linear. Okay, now we're going to go look at strand B. Strand B says that it attacks the cells at a rate that triples every hour. So if it triples, then this is going to be times 3. So 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is 243. And then I'm going to go ahead and continue filling in my table. And I'm just using my calculator to help me with this. All right. And now what I'm going to ask you to do is to graph each of these functions. Can you close that door for me, please? If we were to graph each of these functions, okay, I'm going to start with strand A. In hour 0, it killed 0 cells. In hour 1, it was 50. Hour 2 is 100. Hour 3 was 150, 200, 250, 300. And you can see that this is forming a straight line all the way up to that 500 cells. So again, you can see in another format that this is linear. Now let's look at strand B, okay? In 0 hours, it had killed 1 cell. So I'm just going to put that around there. In 1 hour, it killed 3 cells, so it's low. In hour 2, it was up to 9. In hour 3, it was 27, which is around here somewhere. And I can already see that this is no longer forming a straight line. In hour 4, it was 81, which is around here. In 5 hours, it was 243, which is around here somewhere. All right. So even without plotting every one of the points, you could see that this formed this curve down here that we look for in these exponential models. Okay, that's got that curve that happened, and then it shot up really fast. All right. All right. So that is our example number 13. That's our application problem, where we were really able to compare a linear function from a exponential function all the way through one word problem. And I do just want to come up here and circle again my key phrases in the word problems. So 50 cells per hour told me linear. And then this phrase triples every hour. That was key for me that this was going to be exponential. All right, and now we are ready to finish up with our final example. And I wanted to show you how to do all of this in our calculator. So at the bottom left-hand side of your paper, I wrote these notes on your paper as well. And I just wanted to remind you back from our linear functions unit, our first step was to turn on the diagnostic. How we do that is we do second 0 down, 2 Ds, we find diagnostic on, and we hit enter twice. Our second step is to enter our data. So we go to stat edit and we type that in L1 and L2. And then step number 3, before we used to do stat calc 4 for a linear function. Now today we are going to be doing stat calc 0 for an exponential function. All right. And so we are going to follow these steps in answering this question. So I want you, first of all, to remember how do we choose like which one is going to be a best fit model using our calculator. And if you remember back to our linear functions unit, we were talking about R. Now we have gotten used to referring to R as our core, I'm sorry, not our, as our ratio, okay? But remember before in our calculator, the R is actually the correlation coefficient. And the closer that correlation coefficient is to 1 or -1, the stronger it is. So whichever function, either a linear function or an exponential function that has the stronger correlation coefficient, that is going to be the model that fits it best. All right, so let's go ahead and practice our steps for this. So I'm going to pull out my calculator and turn it on. And I need to go ahead and type in, or actually do step 1 first. Step 1 is to turn on our diagnostic. So here it is. So on, okay, second, 0, second, 0, there it goes. Go down to the D's, and then we are going to go and find diagnostic. So there's the C's. There it is, diagnostic on. Go up one more. Okay, and we're going to hit enter, and then enter again. Let's try this again. So clear all this. Second, 0, down to the D's, diagnostic, on, enter. All right, and then enter again, and that time it worked. Now we are ready to do step 2, which is to enter our data. So stat, edit, and then my X values are 0 through 4, 1, 2, 3, and 4. Go over to the L2 list, which is our Y values, and we're going to type 1, 4, 9, 16, and 34. All right, so there's our data. And now I am ready to get a linear model. Stat, calc, 4, enter. And then I need to look for my correlation coefficient. For the linear model, it is a 0.88. 0.88. Now we're going to do that same process for an exponential model. And we're going to see which R value is larger. So right from here, I'm going to go to stat, over to calc, down to 0. You could just type it, but I want to show you that it says EXP regression, so that's my exponential regression. And my R value here is 0.985. 0.985. So which value is stronger? And that is going to be my exponential. Okay. Another way that we can work with these exponential models is if you go to second, y equals, turn on your stat plot, and then let's go to zoom stat. Remember, that's where we do our statistics, so that's number 9. And here is my data. And you can see that there's kind of a curve function here. It's close, it could be linear, but then this point here kind of goes up a little too far for us to see, okay? A linear model fitting that better. So that's another way that you could kind of determine. But if they're asking for the exact correlation coefficient, you need to use that calculator part to do it, not just looking at the picture. All right. That is it for today's lesson. It was fairly simple, this part of it, and so you may have actually done geometric sequences today as well as linear versus exponential, or your teacher might have chosen just to do one part of the notes. However, either way, you're still going to need to practice. So that is posted for you in Google Classroom. All right, and so get your practice on, and then we are getting ready for a test very soon because we're at the end of our unit. All right, until next time.